Now we'll connect GenAI to real enterprise applications. You'll see how APIs, orchestration, workflows, and backend systems turn models into dependable services, with safety, monitoring, and graceful failure designed in from the start. We've already covered the foundations of production architecture: reliability, security, monitoring, cost, reference layers, and RAG data flow. From here, the focus shifts to integration. The goal is to make LLM capabilities available as enterprise services through governed APIs, orchestration, workflows, and resilient design patterns. The integration layer turns a powerful model into a dependable enterprise capability. Instead of letting every application connect directly to models, databases, tools, and APIs, it creates one controlled path. That path handles authentication, policy checks, input validation, monitoring, and routing. It can retrieve context, call the right model, trigger business workflows, and return a response through a stable contract. It also adds production safeguards such as rate limits, retries, fallbacks, and versioning. With this separation, teams can change models or data sources without rewriting the application. AP-first design means the application does not call a model directly or pass prompts, however it wants. It calls a governed service with clear business endpoints, such as chat, summarize, retrieve, classify, or generate report. That boundary gives teams versioning, monitoring, access control, and predictable contracts. REST is usually the safest public interface because it is browser-friendly and widely supported. gRPC is better for internal microservices that need strict schemas, high throughput, and efficient streaming. The key design move is to expose capabilities, not prompts. Open API, protobuf, and developer portals make those contracts easier to discover and reuse. Before any request reaches the LLM, treat it as untrusted input crossing a security boundary. Start by validating structure, required fields, token size, file types, language, tenant ID, and user permissions. Then confirm the caller's identity using auth, OIDC, API keys, service accounts, or mutual TLS. Next, enforce authorization, which features data, models, and tools this caller is allowed to use. Finally, apply abuse controls such as rate limits, quotas, content filtering, and prompt injection screening. This gateway reduces risk before orchestration begins. LM APIs need stronger contracts than traditional request-response endpoints because outputs are variable and may arrive over time. A good response schema separates the final answer from operational metadata, including citations, confidence, trace ID, token usage, and safety status. For longer interactions, streaming improves the user experience by sending token deltas or progress events before the full response is complete. Use server-sent events for simple browser streams, WebSockets for bidirectional chat, and gRPC when internal services need high performance. Also version more than the endpoint. Version prompts, models, and response fields so downstream systems do not break unexpectedly. Orchestration frameworks provide the application layer around an LLM. They turn one-off prompts into reusable systems with prompt templates, chains, tool calls, retrieval, memory, routing, monitoring, and evaluation. The main difference is emphasis. LangChain is broad and integration-heavy, useful when many tools and agent patterns are needed. Llama Index is strongest when the core challenge is connecting data, indexing it, and building RAG workflows. Semantic kernel fits enterprise environments, especially where planners, skills, and Microsoft integration matter. Haystack is pipeline-oriented and strong for search, question answering, and production retrieval systems. Choose based on workflow needs, not popularity. Frameworks are especially useful when speed matters. Quick prototypes, common model connectors, vector store integrations, and tool calling patterns. In production, though, teams usually need stronger guarantees than a framework abstraction can provide on its own. Custom orchestration gives you stable contracts, repeatable tests, observability, retries, fallbacks, and compliance controls. A common enterprise pattern is not either-or. Use the framework behind an internal service, then expose your own controlled API. That keeps development velocity high while preventing framework details from leaking into long-lived public contracts. A production LLM request is more than a prompt sent to a model. It moves through controlled checkpoints. The API gateway confirms identity, enforces rate limits, routes traffic, and logs the request. The application service validates inputs, resolves tenant context, and applies business rules. The orchestrator brings the AI workflow together through retrieval, prompt assembly, tool use, model calls, and post-processing. Around every step, observability and governance capture traces, metrics, cost, safety signals, secrets usage, and audit records. This control plane is what makes LLM behavior operationally manageable. Function calling turns an LLM from a text generator into a coordinator of actions, so the safety boundary is critical. Define each tool with a strict schema, allowed parameters, clear descriptions, and expected outputs. The model can propose which function to call, but trusted backend code decides whether it actually runs. Before execution, validate arguments, enforce permissions, and respect tenant boundaries. After the tool returns data, validate the result before giving it back to the model. Finally, log every invocation so behavior can be audited, traced, and improved. Agents are useful when the path is not known in advance. They can plan, choose tools, inspect results, and adapt their next step. In production, that freedom needs boundaries. Set maximum iterations, cost and time budgets, approve tools, policy checks, and human approval where risk is high. For regulated or repeatable processes, a deterministic workflow is often safer because every step is predefined and testable. Whichever pattern you use, capture the full execution trace so teams can debug decisions, tool calls, failures, and unexpected cost spikes. When a GenAI process takes minutes, hours, or days, do not run it as one synchronous API call. Use a workflow engine such as Temporal, Airflow, Argo, step functions, durable functions, or Camunda to coordinate each stage. A job can be queued, run extraction, retrieve context, generate a draft, pause for approval, retry failures, and then publish the result. The key is durable state. If a worker crashes, a service restarts, or a reviewer waits overnight, the process can resume with a full audit trail. Production LLM systems need guardrails because each request may depend on several unreliable pieces: a model API, retrieval store, tool, or internal service. Start with timeouts, so one slow dependency cannot consume threads forever. Use retries only for failures that are likely transient, and space them with exponential backoff and jitter. Add circuit breakers when a dependency is unhealthy, so the system fails fast instead of amplifying the outage. Then design fallbacks in advance: a smaller model, cached answer, simplified rules, or graceful degradation. Resilience is not one feature. It is a chain of controlled failure decisions. Not every GenAI request should become a fresh, synchronous model call. Cache anything deterministic or slow to recompute, such as embeddings, retrieval results, summaries, and policy decisions. When demand spikes, move non-urgent work into queues so workers can process generation, batching, or long-running tasks without overwhelming dependencies. If a model or service slows down, degrade deliberately. Offer search-only results, reuse a previous answer, hide an unavailable summary, or route to human review. Most importantly, communicate status clearly, with retry guidance instead of mysterious failure. To make GenAI usable in the enterprise, design APIs first, then orchestrate prompts, retrieval, tools, and model calls behind stable services. For agents and workflows, keep autonomy bounded with audit trails, approvals, and policy controls. Finally, build for failure with timeouts, retries, circuit breakers, caching, queues, and fallbacks. Next, we move from architecture into deployment and platform engineering.